Welcome to Brain Vision.
This is chapter 27, problem number 68. We have a circular loop pivoted about a y-axis. I'm going to draw the problem from the top view. So this would be our positive y direction, and then we would have x here. And again, the circuit is pivoting about the y-axis. So let's say this is the one side of the loop, and the current flowing through that side is 15 amps. Again, this is from the top view. And this would be the positive z-axis then. So this angle is given to us as 30 degrees. And now in part A, we're trying to find the magnitude and direction of the torque to hold the loop in its place, just like this, which means we need to calculate the torque applied by the magnetic field. And then we're going to say the net torque has to be 0. So along the opposite direction, we're going to pick our torque to be to hold this loop in place. So in part A, the direction of the B field is given to us as positive x direction. So the magnetic field is along positive x direction. So let's determine the direction of the magnetic moment. So if the current is going this way, the magnetic moment, let's remember mu equals pi a from the right hand rule. We're going to determine the direction of mu to be this. So if we look at the angle between the two, this angle would be 30 because these two lines are parallel. Then the angle between mu and B here is 60 degrees. So now calculating the torque, mu cross B, of course, but I'm writing down the magnitude, mu B sine of the angle between the two. Mu being I times A, so let's substitute it here. IAB sine theta, then I is 15 amps, area is 0.06. Again, I'm writing this in terms of meters, 0.08 meters times 0.48 Tesla, and sine of 60 degrees. So when we plug everything in, what we find is 0.03 Newton meters for torque. So this is the magnitude. Let's look at the direction now. Direction of this torque can be found applying right-hand rule, right? So from the right-hand rule, if we align our thumb with the direction of mu and the rest of the fingers with the direction of the B field, when we curl our fingers 90 degrees, we get the direction of the torque. In this case, the direction of the torque is going to be into the page being negative y direction. So then this torque is going to be along negative j hat direction, right? However, we want the direction of the torque that holds this loop in its place. So then the net torque has to be equal to 0. Then the torque that we need is the same magnitude of torque to hold it in place, but applied along the opposite direction. So what we're looking for is a torque that has this magnitude that applied along positive j hat direction, right? This is the answer. So in part B, what we have is what happens if B now, magnetic field is along negative z direction, then what would change instead of having the B along positive x direction? So this is negative z direction, right? So if our B this time goes up like this instead of going along negative x direction, then the angle between mu and B, as you can see, this is 60 degrees, so this portion is going to be 30 degrees. Again, what will be the torque? It will be mu B sine theta, mu being I times A, B sine theta. So the current is 15 amps, area is 0.6 meters times 0.08 meters. Magnetic field is 0.48 Tesla. Now this time we have sine of 30. So when we plug everything in, what we find is 0.17 Newton meter. Let's look at the direction. Again, using the right hand rule, our thumb is aligned with the direction of mu. The rest of the fingers are along the direction of B. When we curl our fingers 90 degrees, what we see is this torque is along actually positive j hat direction. So to balance it out, then we have to have the same magnitude of torque, but along negative j hat direction. Then we would be holding the loop in its place. Now, part C is asking what would change, would our answers to part A and B change if the loop was pivoting through an axis that passes through the center of the loop. So you can remember this is positive y, this is this is x. If we have a loop that can rotate around the central point. So look, there will be a torque on both sides. So we would have to consider the torque from this side and this side if the pivot point is between these two points. There would be, let's write it down. There would be torque on both sides. Of the loop, but so the force would be doubling, but the level arm, like instead of having 2L now, we have L over 2, right? This is from here to there, but the level arm would be half, so that the total torque would not change. Right, so the answers to part A and B, if we had the rotation around the middle point of the loop, actually our answers to part A and B would not change.